Welcome to Spring Lib.
We begin with the integers that are not divisible by 3. So let's first of all observe that we can write S as a set. Well, it contains 0, 1, 2. It contains -3, -2, -1 in order. Then it contains 3, 4, 5. Then 6, 7, 8, all the way up to infinity. And then going back, we have -6, -5, -4, all the way back to minus infinity. So now on the first column, we see that we have all the multiples of 3. On the second column, we have multiples of 3 plus 1. And then on the second column, we have multiples of 3 plus 2. So we can essentially divide the set S in 3 different classes, and we're ignoring the red column because those are exactly the numbers divisible by 3. So the numbers in green can be written as 3n plus 1, and the numbers in blue as 3n plus 2, where n is an integer. Since we want to find a bijection between S and the set of positive integers, we need a way of splitting each of the two classes, so green and blue, into two subsets so that we can split the case for positive and negative n. So the trick is to send those into, well, even and odd numbers, but we already have 2 cases, so we need to consider 4 cases. So let's explicitly write the function f that goes from S to Z plus, where now 3n plus 1, so the green column, gets split into 2 subcases, and we have 4n if n is greater or equal than 1. Otherwise, 4 minus n plus 1 if n is lower or equal than 0. And then the other case, 3n plus 2, we send that into 4n minus 1 plus 2 if n is greater or equal than 1, and 4 minus n plus 3 if n is lower or equal than 0. This way, we're actually mapping to, well, we start with 1, then we have 2, then we have 3, and then we have 4, 5, 6, 7, 8, 9, 10, 11, all the way up to infinity, which is exactly all of Z plus. Now for the case of B, we have all the integers which are divisible by 5 but not divisible by 7. So the first thing is to observe that n can be written as 5m and 7 does not divide m. Now, as in the previous case, m can be divided in 7 different classes. So there are the multiples of 7 which we are excluding, and then we have the multiples of 7 plus 1, the multiples of 7 plus 2, all the way to the multiples of 7 plus 6. And they correspond to, well, if m is 7 times k, that's 35k, but we're excluding this case. Then we have 35k plus 5, 35k plus 10, all the way down to 35k plus 30. And there are exactly 6 cases. And again, k now is over the integers, so we need to split between the positive and the negative, and as always, they will be mapped into even and odd positive numbers. So let's write our function. So the first class is 35k plus 5, and again we're mapping those to 12k if k is greater or equal than 1, and 12 minus k plus 1 if k is lower or equal than 0. So this completely takes care of the first class, so 35k plus 5, and we are dividing for k positive and negative, mapping into multiples of k and multiple of k plus 1. Then we do the same with the class of 35k plus 10, which goes into multiples of 12 plus 2 and multiples of 12 plus 3. And we repeat all the way down to the last class, which is 35 plus k plus 13, which goes into multiples of 12 plus 10 and multiples of 12 plus 11. and those cover all the possible cases inside Z+. Now for the case C, we have all the real numbers whose expansion in decimal contains only ones. So a generic element of this set X will be something like 1, 1, 1 up to the comma, and then a bunch of ones afterwards. So we can divide into the number of ones before the comma, which must be greater or equal than 1, because the number is not allowed to start with 0 point something. It must at least start with 1. So it can be like 11 point something, 1 point something. So there's at least one before the comma, and there are m ones after the decimal point, and that's allowed to be 0 because we can write just the number 1 as, well, 1.0, but we just write 1. So let's call these numbers nx and mx because they depend on x. And so let's begin with defining a function g that goes from s to z plus times z plus with 0, which of course maps x to nx and mx. And now it is easier to study because let's list the elements of this set. Let's write them as 1, 0, and then 1, 1, and then 1, 2, 1, 3, 1, 4, and so forth. And then we have 2, 0, 2, 1, 2, 2, and so forth. And then 3, 0, 3, 1, 3, 2, and so forth. So this is a diagonal argument, as we know. So we can say that this is, let's call this the first of the list. Then this is the second, this is the third, going up diagonally. Then we have the fourth, the fifth, and the sixth, when again we're going up diagonally. And then we keep listing them following this diagonal listing. So let's call H the map that goes from Z plus times Z0 plus to Z plus, which encodes this listing following the diagonal listing. And then finally the function we want F goes from S to the positive integers, where X is mapped to H of G of X. And this is the map that we're looking for. And of course this is a bijection because both G and H are bijections. Finally, we have the set of real numbers whose decimal expansion contains only ones and nines. But now we observe that let's fix an X and let's replace every 9 that appears with a 0. We can see this modified number as a number with binary expansion. Vice versa, if we take a number with a binary expansion, we can replace all the zeros with nines, and we obtain an element of S. But now we can write every real number with a binary expansion. There's nothing special about the decimal expansion. So S is in bijection with the set of real numbers written in binary. But this is exactly just R, because again, there's no difference writing in binary or writing in decimal. And so S is in bijection with an uncountable set, and therefore S is uncountable.